In 2019, humanity saw a black hole for the first time. At least, that's what we thought. That image, a glowing orange ring against absolute darkness, the center of galaxy M87, was called a historic moment. The world's biggest newspapers put it on their front pages. Millions of people shared it as final proof that black holes are real. But here is what nobody told you. Technically, that photograph did not capture a black hole. It captured what surrounds a black hole: superheated gas, radiating dust, light bent by extreme gravity. The black hole itself, by precise physical definition, is completely invisible. We have never actually seen it. We only ever see its aftermath. And now, some of the world's leading theoretical physicists are asking an even more radical question. Does what we call a black hole actually exist, the way we think it does? Or is the entire concept a perfect illusion, one constructed by our own equations? If they are right, then it is not just one photograph that needs to be reconsidered. The entire foundation of modern cosmology, how galaxies form, how the universe operates, even the nature of reality itself, would need to be rewritten from the beginning. If you want to keep bending reality with us, subscribe to the channel. Now then, let's begin. Before we question what black holes are, we need to establish what the evidence actually tells us. Because the case for their existence is not built on speculation. It is built on some of the most precise measurements in the history of science. Start with sound. In 2015, two detector facilities in Louisiana and Washington state, collectively known as LIGO, picked up a signal lasting less than 0.2 of a second. That signal was the stretching and squeezing of space-time itself, rippling outward from a collision between two black holes approximately 1.3 billion light-years away. 1.3 billion years ago, two objects each roughly 30 times the mass of our Sun spiraled into each other and merged. The energy released in that fraction of a second exceeded the combined output of every star in the observable universe. We felt it here on Earth as a vibration smaller than 1/10,000th the diameter of a proton. LIGO detected it anyway. That is not a theory. That is a measurement. Then there is light. The Event Horizon Telescope, a planet-sized array of synchronized radio dishes, produced that famous image in 2019, and followed it with an image of Sagittarius A star, the black hole at the center of our own galaxy, in 2022. Both images showed a bright ring of bent light surrounding a central dark region, exactly matching what Einstein's field equations predicted more than a century earlier, before black holes were even considered physically real. And then there is what the James Webb Space Telescope has been showing us since 2022. Webb has detected supermassive black holes existing when the universe was only 400 to 600 million years old. To put that in perspective, the universe is approximately 13.8 billion years old today. These black holes were already enormous when the universe was barely 3 to 4% of its current age. This is where the evidence stops being comfortable. Our standard models of black hole formation cannot explain how objects containing hundreds of millions of solar masses assembled themselves that quickly. The physics we trust, the same physics confirmed by LIGO and the Event Horizon Telescope, does not give enough time for that to happen through known processes. Something in our understanding is either incomplete or wrong. This is the pattern that has preceded every major revolution in physics. The math works perfectly, right up until the moment a new observation reveals it does not work quite well enough. Black holes exist. On that point, the evidence is overwhelming. But what a black hole actually is, at its deepest level, what happens at its boundary, what lives inside it, whether the singularity is real or a symptom of broken mathematics, that is where the science becomes genuinely, uncomfortably open. And that is exactly where we are going next. Here is the problem that has kept theoretical physicists awake for nearly half a century. Physics, as we currently understand it, runs on two separate operating systems. The first is general relativity, Einstein's description of gravity as the curvature of space-time. It governs the very large, planets, stars, galaxies, the structure of the universe itself. It is breathtakingly accurate. Every prediction it has made has been confirmed by observation, often to extraordinary precision. The second is quantum mechanics, the framework describing how matter and energy behave at the smallest scales. It governs atoms, particles, and the forces between them. It is also breathtakingly accurate. The predictions of quantum electrodynamics, for example, match experimental results to within 1 part in a billion. It is arguably the most precisely tested theory in all of science. Two frameworks, both essentially perfect within their own domains. And at a black hole, they collide, and they completely contradict each other. Here is the specific point of rupture. In 1974, Stephen Hawking combined quantum mechanics with general relativity and discovered something that should not be possible. Black holes, he calculated, are not entirely black. They slowly emit thermal radiation, what we now call Hawking radiation, caused by quantum effects near the event horizon. This means black holes lose mass over time. Given enough time, a black hole evaporates completely and disappears. General relativity has no problem with this. An object forms, an object eventually vanishes, clean. Quantum mechanics, however, has an enormous problem with this. One of the most fundamental principles of quantum mechanics is that information cannot be destroyed. Every physical process is in principle reversible. The precise quantum state of every particle that ever fell into a black hole must, according to quantum mechanics, be preserved somewhere. It cannot simply cease to exist. But if the black hole evaporates completely, where does that information go? Hawking radiation, as originally calculated, carries no information about what fell in. It is purely thermal, random, structureless, which means when the black hole is gone, the information is gone with it. This is the information paradox, and it is not a minor technical discrepancy. It is a direct fundamental conflict between the two most successful theories in the history of physics. In 2023, a research group published findings in Physical Review Letters suggesting that information may leak out gradually through subtle quantum correlations in Hawking radiation, a mechanism known as the Page curve. It was a significant theoretical step, but the mechanism required to make this work sits in direct tension with the smooth, continuous geometry that general relativity describes at the event horizon. Solving one side of the contradiction appears to break the other. Physicists use a specific phrase for this situation. They call it a crisis. Not a puzzle, not an anomaly, a crisis. Because what it tells us is that somewhere between the very large and the very small, our picture of reality has a seam, and black holes are exactly where that seam is pulled apart. What lies on the other side of that seam is what the next generation of physics is being built to answer. What follows is not settled science. These are competing theoretical frameworks, each proposed by serious physicists, each published in peer-reviewed literature, and each representing a genuine attempt to resolve the crisis we just described. Hold them as possibilities, not conclusions. The first is the holographic principle. In 1997, theoretical physicist Juan Maldacena published a paper that would become one of the most cited works in the history of modern physics. His proposal, known as ADS/CFT correspondence, suggested something almost impossible to absorb on first contact, that a region of space containing gravity can be completely and equivalently described by a lower dimensional theory on its boundary, a theory with no gravity at all. Applied to black holes, the implication is radical. Everything that falls into a black hole, every particle, every piece of information, may not actually be destroyed inside. It may be encoded, in full, on the two-dimensional surface of the event horizon. The interior, the singularity, the crushing depth we imagine, all of it may be a projection. A three-dimensional experience generated by two-dimensional information, the way a hologram produces the appearance of depth from a flat surface. Think of it this way. Imagine watching a film in a cinema. You perceive depth, movement, three-dimensional space on the screen. But all of that information, every shadow, every dimension, exists entirely on a flat surface. The holographic principle suggests the interior of a black hole may work the same way. What appears to be a deep physical reality may be a projection of something encoded on a boundary we can barely conceptualize. This is not fringe speculation. It is the dominant framework in theoretical high-energy physics today. But it remains unproven by direct observation. The second hypothesis comes from string theory, and it proposes that the black hole interior, as we imagine it, simply does not exist. The proposal is called the fuzzball. Rather than a smooth region of curved spacetime collapsing toward a singularity, string theorists, including Samir Mathur, have suggested that a black hole is better described as an extraordinarily dense, tangled mass of quantum strings, a fuzzball that fills the entire volume we associate with the black hole's interior. There is no empty space inside. There is no singularity at the center. The event horizon in this picture is not a clean geometric boundary, but a fuzzy quantum surface where the strings themselves form the structure. To an outside observer, a fuzzball would be observationally nearly identical to a classical black hole. The mass, the gravitational pull, the orbital dynamics around it, all essentially the same. The difference lives entirely at the quantum level, at scales we cannot yet resolve with any existing instrument. It is worth stating clearly, fuzzball theory has not been confirmed. It is a theoretical construct that emerges from string theory, which itself remains unverified as a complete physical theory. but it offers something classical black hole models cannot, a description of the interior that does not require the mathematics to break down. The third hypothesis is perhaps the most quietly unsettling. In 2001, physicists Paul Mazur and Emil Motola proposed an alternative compact object called a gravastar, a gravitational vacuum condensate star. In this model, there is no singularity and no event horizon in the classical sense. Instead, as matter collapses under extreme gravity, it undergoes a quantum phase transition and becomes a shell of ultra-dense matter surrounding an interior filled with dark energy in condensate form, a region where the geometry of spacetime is effectively reversed. From the outside, a gravastar is, for all practical purposes, indistinguishable from a black hole. The same gravitational lensing, the same orbital behavior, potentially the same signatures in gravitational wave data, and this is the part that should genuinely unsettle you. Three completely different internal structures, three different answers to what a black hole actually is at its core. And right now, with the instruments we currently have, we cannot tell them apart from the outside. The universe has given us an object that looks identical from every angle we can currently observe, and left the question of what it actually is completely open. That is not a failure of science. That is science working exactly as it should, standing at the edge of what it currently knows and looking out into the dark. Let us pull this out of the cosmos for a moment and bring it somewhere closer. Right now, as you are watching this, every atom in your body is obeying quantum mechanics. The electrons orbiting the nuclei of your cells exist in states of superposition, not fixed, not definite, but spread across a cloud of possibilities until an interaction forces a resolution. The same framework that breaks down at the edge of a black hole is the framework that governs the chemistry keeping you alive at this exact second. The information paradox is not an abstract problem happening 30,000 light-years away at Sagittarius A star. It is a question about the most fundamental rule of the universe, that information cannot be destroyed, that every physical state has a history, that nothing is ever truly erased. Now make it personal. Every memory you hold, every experience that shaped you, every decision that brought you to this moment, at the physical level, all of it is information. Patterns of matter and energy arranged in specific configurations inside your brain, your body, your nervous system. If the universe genuinely preserves all information, then in some deep physical sense, nothing that has ever happened to you is gone. It is encoded somewhere in the state of the universe. But if a black hole can erase information completely, if Hawking was right in his original calculation, then the universe does not keep records. Things can end without a trace. You are made of the same physics that cannot answer this question. That is not meant to be frightening. It is meant to be honest. The crisis at the heart of black hole physics is not separate from you. It runs through you, and the scientists losing sleep over it are not just trying to understand distant objects in space. They are trying to understand whether reality itself has a memory. To be fair to the other side, let us steelman the case for the standard model. The classical description of black holes has not survived this long by accident. It has survived because it works repeatedly, precisely, and across wildly different observational contexts. When the Event Horizon Telescope released its image of M87 star in 2019, the bright ring of bent light matched Einstein's predictions to a degree that was almost uncomfortable in its precision. A theory written in 1915, before black holes were even considered physically plausible, described the shape of that image with extraordinary accuracy. When the same telescope imaged Sagittarius A star in 2022, the result was the same. The geometry held. LIGO tells the same story. Every gravitational wave signal detected from black hole mergers since 2015 has matched the waveform templates derived from general relativity, not approximately, not close enough, exactly within measurement uncertainty. The universe, at every scale we can currently probe, behaves precisely as Einstein said it would near a black hole. So, the defenders of the standard model have a reasonable argument. If the theory produces correct predictions at every point we can test, what justifies replacing it with something more exotic? This is where history becomes instructive. For roughly 200 years, Newton's law of gravitation was the most successful physical theory ever written. It predicted planetary orbits, tidal forces, the trajectories of comets. It was confirmed observation after observation. And then astronomers noticed that Mercury's orbit precessed slightly more than Newton's equations allowed. A tiny discrepancy, almost negligible. But it was real, and it would not go away. That small anomaly was not a measurement error. It was a signal that the theory, however successful, was incomplete. Einstein's general relativity resolved it, and in doing so, replaced 2 centuries of certainty with something deeper. Newton was not wrong. He was accurate within the domain his tools could access. The moment observations pushed beyond that domain, the cracks appeared. We are likely in an analogous position today. General relativity is not wrong in any domain we can currently test, but the James Webb Space Telescope is showing us black holes that should not exist at the ages we are finding them. LIGO is accumulating merger data that may eventually reveal subtle deviations from classical predictions. The universe does not care how elegant our equations are. It has never once adjusted its behavior to match our expectations. It did not do so for Newton. There is no particular reason to believe it will do so for Einstein. So where does this leave us, and where does the science go from here? The next decade of physics has a specific shape. There are instruments being built right now, missions being planned, arrays being expanded, each one aimed, in its own way, at the questions we have been sitting with throughout this video. And for the first time in the history of black hole research, we are close enough to the edge of resolution that the answers may actually arrive within a human lifetime. The most significant development on the horizon is LISA, the Laser Interferometer Space Antenna, a joint mission between the European Space Agency and NASA. LISA is designed to detect gravitational waves from space itself, using 3 spacecraft separated by 2.5 million kilometers, forming a triangle in orbit around the Sun. Unlike LIGO, which is sensitive to the high-frequency collisions of stellar mass black holes, LISA will detect the low-frequency gravitational waves produced by supermassive black hole mergers, the kind of events that reshape entire galaxies. Current planning targets a launch window around 2035. If fuzzball structures or gravastar configurations produce even subtly different gravitational wave signatures than classical black holes, LISA has a realistic chance of detecting that difference. Closer in time, the next-generation Event Horizon Telescope, known as the NGHT, is expected to reach full operational capability somewhere between 2027 and 2030. With a resolution approximately 4 times greater than the array that produced the 2019 image. The NGHT may be able to image structures near the event horizon at a level of detail that could distinguish between competing models. If the boundary of a black hole is a clean geometric surface, it will look one way. If it is a quantum fuzz of string-like structures, it may look another. And the James Webb Space Telescope continues operating, accumulating data on black holes in the early universe that our current models cannot fully explain. Every new observation is a constraint. Every constraint narrows the space of viable theories. The answers are coming. Slowly, carefully, the way science actually works. Not in sudden revelations, but in the gradual accumulation of evidence that eventually makes one picture undeniable and another untenable. But here is what no telescope will ever fully resolve. Even if we determine precisely what a black hole is made of at its boundary, even if we confirm or rule out the holographic principle, even if we close the information paradox, we will still be left with the deeper question that black holes have always represented. Not a physics question, a philosophical one. We are a species that builds instruments to look at things we will never visit, to measure events that happened before our planet existed, to test ideas about the nature of reality using mathematics developed by human minds that evolved for an entirely different purpose. And somehow, improbably, it works. Not perfectly, not completely, but well enough to keep pushing the boundary of what is knowable. A black hole, whatever it ultimately turns out to be, is the universe's most honest mirror. It shows us exactly how far our understanding reaches and exactly where it stops. Maybe it is an illusion. Maybe it is something stranger than any word we currently have for it. What do you think changes in science or in the way you see the world if the answer turns out to be something none of us expected?